In a quiet industrial park in Massachusetts, engineers are building a machine that could rewrite the future of energy. It is not a power plant in the traditional sense. It is something far more ambitious. Inside a steel chamber cooled to nearly absolute zero, scientists are preparing to recreate the same reaction that powers the sun. This is fusion energy, and for decades it has lived in the realm of science fiction. Now, in the United States, a new generation of reactors is bringing that dream closer to reality than ever before. One project, built by a company called Commonwealth Fusion Systems, is racing toward a milestone that could prove fusion power is not just possible, but practical. If it succeeds, this technology could one day help deliver clean, nearly limitless electricity to homes across the country. But the road to get here has taken decades, billions of dollars, and a level of engineering few people fully understand. This is the story of America's new fusion reactor and why so many scientists believe it could change everything. For more than 70 years, scientists have chased the same goal, harnessing fusion, the reaction that powers every star in the universe. Unlike the fission reactors used in today's nuclear plants, fusion works by forcing atoms together instead of splitting them apart. When light atoms like hydrogen fuse into heavier ones, they release enormous amounts of energy with almost no long-lived radioactive waste. The problem has never been the concept. The problem has been control. Recreating star-like conditions on Earth requires temperatures hotter than the core of the sun itself. For decades, research reactors could create fusion reactions, but they consumed more energy than they produced. That changed in December 2022, when the National Ignition Facility in California achieved a reaction that released more energy than the lasers put into it. It was a historic proof that net energy fusion was scientifically possible, not just theoretical. That result reignited global interest, and private companies in the United States began racing to turn the science into real machines. One of the most closely watched is Commonwealth Fusion Systems, a company that grew out of research at MIT. Founded in 2018, the company set out to build smaller, more affordable fusion reactors using a new kind of magnet technology. Their approach centers on a demonstration reactor called Spark, now under construction in Devens, Massachusetts. The goal of Spark is not to generate electricity for homes yet. It is to prove, once and for all, that a compact fusion reactor can produce more energy than it consumes. The threshold is known in physics as break-even, or a Q value greater than 1. If Spark hits that mark, it would be one of the most important energy milestones in modern history. So how do you actually build a machine that recreates the power of a star? Spark is a type of reactor called a tokamak, a donut-shaped device first developed decades ago by Soviet physicists. Inside the donut-shaped chamber, hydrogen fuel is heated until it becomes plasma, a superheated cloud of charged particles. At full operation, that plasma can reach temperatures many times hotter than the core of the sun. No physical material could ever touch plasma that hot and survive, so engineers use something else to contain it: magnetic fields. Powerful magnets surround the chamber, holding the plasma in place without any physical contact at all. The stronger the magnetic field, the smaller and more efficient the reactor can be. This is where Spark's key innovation comes in: high-temperature superconducting magnets. These magnets are built from a special tape-like material that can carry enormous electrical currents with almost no resistance, but only when cooled to extremely low temperatures. Cooled to nearly minus 253 degrees Celsius, these magnets can generate magnetic fields many times stronger than a typical hospital MRI machine. That extra strength is what allows engineers to shrink the reactor down to a fraction of the size older fusion designs would require. SPARC's design uses 18 of these superconducting magnets arranged to form the reactor's core structure. Each magnet weighs about as much as a loaded truck, and together they create the magnetic cage that will confine the plasma. As of mid-2026, the reactor is roughly 80% assembled, with all 18 magnets expected to be installed by the end of the summer. Once complete, engineers will begin the process of creating the reactor's first plasma, a milestone the company is targeting for 2027. If that plasma reaches the right density, temperature, and confinement time, the fusion reaction inside could release more energy than it took to create it. To help manage the enormous complexity of the machine, engineers have also built a digital twin of Spark, a detailed virtual simulation created with advanced computing partners. This digital model allows the team to test scenarios and predict performance before running expensive real-world experiments. It is a reminder that modern fusion research is not just plasma physics. It is materials science, cryogenics, and advanced computing working together. If fusion energy becomes commercially viable, the impact could reach far beyond a single power plant. Fusion fuel comes primarily from hydrogen isotopes, which can be derived from water, making the fuel source abundant. Unlike fossil fuels, a fusion reaction produces no carbon emissions during operation. And unlike traditional nuclear fission, fusion does not produce the same long-lived radioactive waste and carries a much lower risk of runaway reactions. That combination is why so many scientists see fusion as a potential long-term answer to the world's growing demand for clean power. Commonwealth Fusion Systems is already planning its next step, a commercial-scale power plant called ARC, proposed for a site in Virginia. That plant is designed to eventually deliver around 400 megawatts of continuous electricity, enough to power hundreds of thousands of homes. The company has already signed early agreements with a regional utility and several major investors interested in purchasing future power output. Beyond electricity, a working fusion industry could reshape entire supply chains, from superconducting materials to specialized manufacturing. It could also strengthen America's position in the global race for next-generation energy technology, alongside major public projects like the International Reactor. Universities and national laboratories continue to play a major role too, feeding new research into private efforts like Spark. Investors have taken notice. Commonwealth Fusion Systems has now raised billions of dollars in private funding, including support from pension funds and sovereign wealth investors. That kind of institutional investment suggests fusion is increasingly being treated less like a science experiment and more like future infrastructure. Still, it is important to be clear, none of this means commercial fusion power is guaranteed or that it will arrive quickly. The technology could still take years or even longer to move from demonstration to widespread use. Despite the progress, fusion power still faces serious engineering hurdles. Even if Spark achieves net energy gain, that is a scientific milestone, not a finished power plant. Turning short bursts of fusion energy into a steady, reliable stream of electricity is an entirely different engineering challenge. The materials inside a fusion reactor must withstand extreme heat, radiation, and magnetic stress for years without failing. Researchers are still working to develop components that can survive that punishment at commercial scale. Fuel supply is another challenge. Certain fusion reactions require a rare hydrogen isotope called tritium, which is not abundant and must be carefully managed. Some future reactor designs plan to breed their own tritium fuel internally. But that process is still being tested and refined. Cost is also a major factor. Building precision magnets, cryogenic systems, and containment structures is extremely expensive. Even optimistic timelines put a fully operational commercial fusion plant in the early 2030s at the very earliest. Regulatory approval adds another layer of complexity, since fusion power plants will need new safety and licensing frameworks. And history has taught the energy industry to be cautious. Fusion has often been described as a technology that is always a few decades away. Researchers today are quick to point out that this project could still face delays, technical setbacks, or unexpected obstacles. In short, the science increasingly looks promising, but the engineering and economics still have real work ahead. So what happens next on the path to commercial fusion? In the near term, all eyes are on Spark's first plasma test, expected in 2027. If that test succeeds in reaching net energy gain, it would mark one of the most significant milestones in the history of energy research. From there, attention would shift to the ARC power plant in Virginia, which developers hope could begin supplying electricity to the grid sometime in the early 2030s. Commonwealth Fusion Systems is not working alone. Other American companies are also pursuing different approaches to fusion, using alternative reactor designs and fuel combinations. Some are backed by major technology companies exploring long-term power purchase agreements for future fusion electricity. This growing competition could accelerate innovation, as different teams test different engineering solutions in parallel. Government agencies are also involved, funding research into materials science and reactor engineering that could benefit the entire industry. If even one of these projects succeeds commercially, it could open the door for a new global energy industry built around fusion power. Over time, researchers hope that costs could fall, materials could improve, and fusion plants could become smaller and more efficient. It is still too early to say exactly when fusion will become a mainstream part of the energy grid. But for the first time in decades, fusion energy is being discussed not as a distant fantasy, but as an engineering project with real deadlines. Fusion power has been called humanity's oldest energy dream, the idea of bottling the same reaction that lights up every star in the night sky. For most of the 20th century, that dream stayed just out of reach. Today, in a facility in Massachusetts, engineers are turning decades of theory into welded steel, superconducting magnets, and carefully engineered plasma. No one can say with certainty when fusion will power the average American home. But projects like Spark represent something rare in the history of energy, real, measurable progress toward a goal once thought impossible. If this technology succeeds, it could mark the beginning of a new chapter in how the world powers itself. And it all started with a simple question that scientists have asked for generations. What if we could build a star right here on Earth?